when we try to look at a quantum mechanical description of a bond. I think this roadmap is one of my best as it shows how the ideas are related. We saw that we could begin with a simple picture of bonding involving Lewis structures, and that was helpful to be able to predict what the geometry when we applied Vesper theory. When we're thinking about bonds, we've also, though, have some understanding. I've been spent a lot of time of describing atomic orbitals. We looked at aspects of their shape, the electron configuration, using the Pauli exclusion principle to inform that, and the resulting orbital diagrams. Now what we're going to do is we're going to bring together these ideas, bring together aspects of the geometry, and use atomic orbitals in an approach called valence bond theory. So we're going to find that the bonds that we'll be forming will characterize as sigma and pi bonds. Those definitions arise based on their shape. We're going to find that when we use valence bond theory, sometimes we're going to have to change the electron configuration by promoting electrons and making hybridized orbitals. These will still be using the language of sigma and pi bonds. And the kinds of hybridized orbitals we're going to make will have symbols sp, sp2, and sp3. There'll still be sometimes leftover unhybridized orbitals in our analysis, and we'll see those lead to pi bonds, and those have implications for whether the molecule can rotate. So within a perusal here, within valence bond theory, I start by noting that we spent a lot of time looking at quantum mechanics. Let's now bring that and connect it to an advanced model for bonding. So we want to be able to characterize how sigma bonds, pi bonds are described, how they're formed. We want to use that and include the idea of hybridization and use it for simple molecules like NH3, CH4, H2O. Valence bond theory is going to be really useful for those types of molecules. So where did we start the story? When we looked at covalent bonds, we said that we were able to have electron density found between the atoms. So when we took our Lewis symbols and made these simple dots, we would say that they could be shared between the atoms. So what did the dots represent? Well, for hydrogen, it was one valence electron. And that when we brought the two atoms together, now we were placing those two valence electrons between the atoms. But we know more than that. Electrons, as we've seen, are in atomic orbitals. So now what we need to do is have a bonding theory that describes how we can combine the atomic orbitals to describe the formation of bonds and the resulting electron density that's found between the nuclei. So we've been discussing this idea of electron density being found between the two nuclei. With valence bond theory, we can now think, what does it mean to bring together the atoms and have overlap of the orbitals that the electrons are found in? So instead of having them be dots, we're putting them back to being in atomic orbitals. And we're going to see how those atomic orbitals now can overlap with each other when a bond is forming. This idea of how many electrons will be placed, we're going to put two electrons of opposite spin to form a given bond. If that sounds like the Pauli exclusion principle, it's because it is. So we'll be looking with our bond formation as the overlap increases. Stronger bonds with lower potential energy are ones where we have stronger overlap of these atomic orbitals, allowing electron density to be the glue that's found between the nuclei. So we need to consider the shape of the orbitals, their orientation, and how they can overlap. So the simplest one would be two hydrogen atoms. They're both 1s atomic orbitals. If I bring those together, if one electron is spin up and one is spin down, that would allow me to place them in this region for the overlap. In something like HCl, I can now see that I have the correct orientation if I have an s orbital and the p orbital that's along that axis. That will allow the overlap. So if in that region I have an electron spin up, an unpaired one spin down, that's what will be described in the bonding region. Two p orbitals, I once again would have the correct orientation. For a chlorine atom, I have an unpaired electron. So if I have both of those, I could bring them together. If one spin up, one spin down, I would see that I have a spot where they could be providing electron density between the two nuclei. So I guess right now what I'm considering, tell me about the atomic orbitals. How will they be situated? What's the orientation relative to where the bond's forming? And do I have unpaired electrons? So with an Atkins, this is how he's describing the bonding in HF and F2. The bonds that are forming here are what are called sigma bonds. They're putting electron density along the internuclear axes. That's our definition for what a sigma bond is. It could be, we've just seen, two s orbitals, two p orbitals, an s orbital and a p orbital. It all depends on the orientation. What about the bonding in N2? So bonding within N2, in each case we start with our p orbitals having three unpaired electrons in it. So if we bring one nitrogen atom together with another one, if one set spin up, another one spin down, in each case, we can be pairing up the electrons in the corresponding orbitals. One would be with the p orbital directly pointed to the other p orbital. That would form a sigma bond. But we've got two options where they can be off axes, either above and below or front to back. When those come together, those are forming now what are called pi bonds. So our definition for a pi bond is when we have electron density away from the internuclear axis. So notice our definitions here. It's all based on where we're finding the electron density. If I look at something with a Lewis structure here like N2 and I try to interpret these dots, what is this telling me now? I think it's saying for a given nitrogen atom, I've got a total of 2, 4, 6 electrons contributing to the bonding. I think I would have overlap of a p orbital with another p orbital to form a sigma bond, overlap of a p orbital with a p orbital that's off the axis to form a pi bond, overlap of a p orbital with a p orbital that's 90 degrees to that's off the axis, that would form a pi bond. And finally, I've got a lone pair of electrons that's not involved with the bonding. Valence bond theory also includes the idea of hybrid orbitals. So far the bonding that we've been looking at, we can just take the orbitals that are found at the atoms, see how they overlap with the neighbor to form a bond, and it's worked. Hybrid orbitals, those are going to explain electron domain geometries that we can't account for with this initial approach. Let me show you what I mean. So our plan is going to be that we're going to first consider a Lewis structure, use that to determine a VSEPR predicted geometry, and then we're going to explain that geometry using valence bond theory. So let's notice the order here. We don't have to do anything fancier than this. We're going to see that it works if we start with a Lewis, then apply VSEPR, and then move to valence bond. I'm going to work through several examples for that. So we first have to start with the correct Lewis structure. So let's say I'm looking at BeF2. I've got the choice of, well, do I complete octets around the beryllium, or do I have less than an octet, but I keep the formal charge of 0 on the fluorine? I'm definitely going to choose 0 on the formal charge of the fluorine. Most electronegative, I'm not going to be finding double bonds with fluorine. So this would be my correct Lewis structure. What's the geometry? I think I see two electron domains, one to the left and one to the right. So it's a linear arrangement, 180 degrees. So if I begin to say, well, how could I situate this and make it work? Well, I know that the fluorine, they're easy to accommodate. Each of the fluorine has a p orbital that could be aligned towards the center, that has an unpaired electron. So for each of the fluorine, it's easy for me to say how it would lead to the correct overlap for a sigma bond. The beryllium, though, is challenging because its initial electron configuration would be 2s2 and nothing in the p orbitals. So this is challenging because right here, how do I end up with unpaired electrons that can lead to the overlap and form the sigma bonds that are initially all paired up? So I'm going to change it a little bit. I'm going to promote an electron, so now I have two unpaired electrons. I'm going to move it to a slightly higher energy level. And then my work isn't finished. I'm going to combine both of these because I don't want a distinct s orbital and a distinct p orbital. That will not be sufficient to explain how I have two equivalent bonds on each side. So I'm going to combine them. I'm going to form two sp hybrid orbitals by mixing together an s orbital and a p orbital. So notice, first of all, the total number of orbitals here on the beryllium has stayed the same. I started with 4, I still have 4. But I'm calling this grouping here 2sp hybrid orbitals because I'm going to need that then to accommodate the actual 2 equivalent sigma bonds that I'm forming. Let's look more of what does it mean to combine and make these hybrid orbitals. So I'll come back to the point, if we know the electron domain geometry from our VSEPR analysis, we're going to know what the hybridization is. So within this case right here, if we need to explain a linear arrangement for the electron domain geometry by combining an s orbital with a p orbital to make 2 sp hybrid orbitals, that's what I show here, that will account then for the overall atomic orbitals that I need. So I'm making each of these, and then one of them's like pointed to the right and one of them's pointed to the left. The 2 sp hybrid orbitals are being used to explain 2 electron domains. What if I have 3 electron domains? Well, that would be a trigonoplanar arrangement. That's explained by having an s with a p to make these 3 sp2 hybridized orbitals that are all pointed 120, 120, 120 from each other. If I wanted to explain a tetrahedral electron domain, I would combine an s with a p to form 4 sp3 hybridized orbitals, and those would now be arranged in a tetrahedral. This idea of saying, how am I combining them? That's going to be useful once again by saying, what is the electron domain geometry? How many atomic orbitals will I be using? And then what will the resulting hybridized orbitals be? We're going to find that this is really going to be a great approach that we're going to use up to a tetrahedral. Could we use it beyond? Yeah, but I don't think this is going to be our optimal bonding theory that we're going to use for beyond. It's going to do great for up to a tetrahedral. That's why this is such a workhorse in organic chemistry. Bonds with nitrogen, carbon, oxygen. It's going to do a fantastic job with that because those have up to a tetrahedral electron domain geometry. Now, when we take our atomic orbitals, let's step back and think about them. So a wave has a sign. When we looked at our different wave functions for a particle in a box, they're going up and down, up and down. And at a given point, we'd have one region with a positive phase and one region with a negative phase. This also was present when we were looking at our wave functions. Here I show one for a p orbital. At a given point, one region's up, one region's down. They have a different phase. We lost this information when we squared it. When we squared it and turned it, the wave function squared to get the probability of finding the electron, we lost the phase information. Everything became positive. But back to the original wave functions, they have a phase. They have a positive region and a negative region. This is what we are now using when we're combining the wave functions that are initially describing atomic orbitals to describe these new hybrid orbitals. We're seeing that we're back to saying wave functions are waves. There's different ways that we can take linear combinations to put them together. This idea of different linear combinations, same thing that I mentioned in class when we were looking at the Pauli exclusion principle. So this idea then of mathematically combining them in different ways, let me see if I can show you symbolically here. So let's say we're combining s orbital with a p orbital to form these sp hybrid orbitals. The sign here is trying to designate the phase. So in this case, the s orbital at this moment is positive, and the p sub x has both a negative lobe and a positive lobe. So try to visualize this, because this is something that we're also going to use with molecular orbital theory. Let's say that we try to visualize taking that s orbital and putting it right here on the top. What would it have? Well, I would see a positive with a positive overlapping and increasing on the right-hand side, and a positive and a negative diminishing on the left. That's why we see this asymmetry to the lobes. We could do that with one combination, and the other would be to flip the phase. This is what it means to say within our linear combination, we've got both options. So we're forming the sp hybrid orbitals. We have two different ones where the lobes have resulted from both constructive and destructive interference. Same kind of thing if we're looking at ones to form our sp2. I find this one a little bit more difficult to visualize. What does it mean to have them off axes like this? But it's the same kind of mixing that's taking place. Now, we might ask, well, why does this happen? We've said that we're going to mix the orbitals to accommodate a particular electron domain geometry, but that seems like it's sort of backwards. How did it know it needed that particular set of hybrid orbitals? I find that I can connect it to this picture of this kid in the bathtub. What we are doing is we are changing the boundary conditions. When we looked at our initial wave functions and we described those as being standing waves in 3 dimensions, those were for a particular set of boundary conditions, meaning certain number of protons, certain number of electrons, certain number of interactions, shielding, etc. All of those details that we were looking at earlier, we first set those up for the hydrogen atom, and then we considered how they would then be also applicable for multi-electron. We're doing something different here. We're now saying, well, what are we seeking to describe? Not individual atoms, but a combination of atoms that are now approaching each other and leading to a bond. So we're changing the boundary conditions. It's like this kid in the bathtub initially. If he's wiggling, there might be standing waves established given those set of conditions. But if you change it, if you put a barrier or something in here, you'll end up with new standing waves, but with a new set of conditions. So what we're seeing is that depending on the number of neighbors that approach, depending on the electron domain geometry, that's what we're seeking to accommodate with these hybrid orbitals. So we're going to start with the Lewis structure, get the VSEPR predicted geometry, and then explain that with valence bond theory. So let's see some examples. So within BF3, that central atom, I need to explain bonds in 3 directions and no lone pairs. It's a trigonoplanar. Trigonoplanar, I would identify initially in my head as sp2. Then let's see what that means in terms of the orbital diagram. This would be a boron initially, 2s2, 2p1. I know that I'm going to take it to sp2. So I'm going to make 3 sp2 hybridized orbitals. I've got a total of 1, 2, 3 electrons to put them in there. Excellent. These will now describe the 3 different sigma bonds that I can form, and they are in the correct trigonoplanar geometry. How do I know they're in a trigonoplanar geometry? Because that's what sp2 leads to. This description here from Peruzzo, same thing is described for what happens with carbon. I like the comment here where upon reflection, yeah, we know carbon forms 4 bonds all the time. That's what's taking place within carbon. We have hybridization involved. I also like this comment here of looking at the energetics. One thing I would add to this, though, let's remember that when we're looking at the overall energetics, it's not for the bare atom, it's for this new collection of atoms as they've come together and we're describing the bonding arrangement. Just like when we were looking at ionic bonds, we said there were energetics involving the electron being removed with the ionization energy, being added with the electron affinity, but we only made sense of the overall energetics. Same thing here. We're making sense of the overall energetics. So let's consider this one. Let's say we're looking at NH3. So with NH3, we can start with the Lewis structure. We know that we have a description with VSEPR where it's a tetrahedral for the electron domain geometry. It's not a tetrahedral for the molecular, though, because of that lone pair. So this is where nitrogen starts out. This would be when it's hybridized. So the question is, well, do we need to hybridize it in this case? Does this initial description work? It works to some extent. I like that I see 3 unpaired electrons because I need to form 3 sigma bonds. So far, so good. I see 2 that are paired up that could be the lone pair. So far, so good. But now with Atkins, he says, you better hybridize it. Well, what are we missing here? Notice within our analysis, this is a tetrahedral. We need to have atomic orbitals that will describe a tetrahedral. The initial s orbital with a p and a p and a p, that does not describe bond angles of 109.5. That describes, if we just think about the p orbitals, they're all 90 degrees to each other. That would not be a tetrahedral geometry. So we need to recognize that when we have this mixing for the hybridization, we need to explain the electron domain geometry not just in terms of the number of bonds or lone pairs, it needs to explain the bond angles too. So we're going to hybridize it, because if we have sp3 hybridized orbitals, they're now all arranged 109.5 from each other. That can be saying there's a lone pair, sigma bond, sigma bond, sigma bond. It's explaining the bonding and the correct geometry. How about something like water? If we look at that central atom, we'll pause and say, okay, that central oxygen atom, it's a tetrahedral. Lone pair, bond, bond. So if we start out with the orbital diagram here for oxygen, we know where it's going to take us. If we have a tetrahedral, we know that it has to be sp3. Then if we populate it, we've got 1, 2, 3, 4, 5, 6 electrons. Let's put them in there and recognize that now within that tetrahedral, lone pair, sigma bond, sigma bond. So for all of these, the important first step is we need to identify what the geometry is so we can identify the hybrid orbitals that we would be using. In this case, if it's a tetrahedral, it's sp3. If it's a tetrahedral, it's sp3. If it's a trigonal planar, it's sp2. Notice carbon, in one case it's sp3, in one case it's sp2. This is where carbon starts out. If I group it to make it sp3, I can explain 1, 2, 3, 4 sigma bonds. If I group it so it forms trigonal planar, got something a little bit different. Sigma bond, sigma bond, sigma bond. That's what the sp2 geometry is being explained by. Notice with carbon now I have a leftover p orbital with an electron in it. We're going to see that that's going to be used to form this double bond. When I look at this broader set, I'm going to jump ahead here. This is describing the bonds that are being formed in each case. You notice that we have many sigma bonds. That's what the single line looks like. But we've got an example of a double bond and a triple bond. Those multiple bonds, where do they fit within valence bond theory? Let's take a look at that. So we saw that a p orbital can overlap with another p orbital to form a sigma bond. But if I have the p orbitals that are off the axes, this is what leads to a pi bond. A pi bond has electron density off of the axes, whether that's above and below or front to back. So within our description right here, sigma bond is generally the first one that we'd write. The second one becomes a pi. The third one becomes a pi. This example right here, let's take a look at this. This is going to require hybridization to explain the fact that these are trigonal planar carbon atoms and a pi bond is present. Let's see how that happens. So this would be that description for what's taking place. I have a double bond between the carbons and then other single bonds. I'd pause and say, okay, this carbon atom, this is trigonal planar, so it's sp2. In each case, though, there's a p orbital that's going to be left over and used for the pi bonding. sp2 is describing trigonal planar arrangement that will explain a sigma bond, and a sigma bond. In each case, though, I have a leftover p orbital that has a single electron in it. That leftover p orbital is perpendicular to the sp2. Aha, that can now lead to the resulting pi bond formation with electron density above and below the plane. Notice that it also restricts the motion a little bit, because those sp2, initially with a single bond, a single sigma bond, I think that bond could rotate around. But notice, in order to have the p orbitals correctly align, they need to match up. They need to be above and below the plane. So that now is serving to make this a rigid molecule. It can't rotate and spin around because then you'd be breaking that pi bond. So I know I've laid a lot of ideas on you here. But we found that by simply doing our analysis of, let's start with the Lewis structure, then VSEPR, identify hybridization, we could then find that we would have the correct orbital diagrams that we could use to describe the bonding. And a key idea here is that because we have this unhybridized p orbital with an electron in it, it would lead to the formation of a pi bond, and it would now restrict the motion. What I'd like to leave you with is, let's consider the bonding here in this one. So this would be the start. I need to draw a Lewis structure. Okay, this is my Lewis structure. A single bond between hydrogen and carbon, triple bond between carbons, and then a single bond between carbon and hydrogen. What I'd like you to think about, see if you can work on, how would we use valence bond theory to explain the bonding in this? How is valence bond theory going to explain the overlap of atomic orbitals that will result in this combination of geometry and bond order? See if you can do that, and then we'll pick up and move from there to look at other aspects of valence bond theory and also molecular orbital theory.